Imagine pulling a steel specimen in a tensile testing machine. At first, it stretches elastically and returns to its original shape. As the load increases, permanent deformation begins at the yield strength. Surprisingly, the material can still carry additional load until it reaches the ultimate tensile strength. Understanding these 2 points is essential for engineering design. The stress-strain curve is obtained from a tensile test. The linear region represents elastic behavior. Yield strength marks the start of permanent deformation. Beyond this point, the material enters the plastic region and continues to deform while carrying higher loads. The curve reaches a maximum at the ultimate tensile strength before necking and fracture occur. Yield strength is the stress at which permanent deformation begins. Below this limit, the material behaves elastically and fully recovers when unloaded. Above it, permanent strain remains. For most engineering components, yield strength is the primary design criterion because loss of shape or alignment can occur long before actual fracture. Ultimate tensile strength, or UTS, is the maximum engineering stress a material can withstand during a tensile test. It represents the highest load-carrying capacity of the specimen. Beyond this point, necking begins and the effective cross-sectional area reduces. Although deformation continues, failure is approaching rapidly. Yield strength marks the beginning of permanent deformation. Ultimate strength marks the maximum stress reached during loading. Between these 2 points lies the plastic region, where the material continues to deform while still carrying additional load. In ductile materials, this region provides warning before failure and improves structural reliability. After reaching UTS, deformation becomes localized in a small region called the neck. As the cross-sectional area reduces, stress concentration increases. Microvoids form and grow until cracks develop. Eventually, the remaining area can no longer support the load, resulting in fracture. This is the final stage of ductile failure. Consider a crane hook lifting a heavy load. If stress exceeds yield strength, the hook deforms permanently and may become unsafe even though it has not broken. If loading continues toward ultimate strength, crack initiation and sudden failure become possible. This is why engineers design using yield strength and appropriate safety factors. Yield strength tells us when permanent deformation begins. Ultimate tensile strength tells us the maximum stress a material can withstand. A component can yield long before it fractures. For this reason, engineers design to remain below the yield point, ensuring safety, functionality, and long-term reliability. If this video helped you understand yield strength and ultimate strength, hit the like button and subscribe for more engineering concepts.